Okay, good evening again. Few announcements. First, next week we will have a class, but on the July 15, we will not have a class. Instead, we will have a class on July 22, which is a week after. And if needed, it will be a longer class because everyone will present their project. So it is expected that everyone will be present, and you will be required also to give feedback on the presentation of each one. So the idea is that you are presenting in order for the others to learn, not to get grade, but to learn from what you are presenting. You also will get grade, but that's for the work that you submit. So everyone is expected to be on July 22. And for those that did not wrote themselves on the Excel sheet, the Google sheet that I sent in the mini project that you have to assign yourself and write what the project you are doing. Please do this as soon as possible because according to this, I'll set the timing for presentation. So that's important as well. So that's it. And today we will talk about this week and next week. We will talk about control. And this is the last subject of the course. So let's start. Do you see the screen? No. Okay, good. And now it's also recording. Great. So, in the past two lectures, we talked about the dynamics of the system. And we talked about Lagrange equation of motion, and eventually we'll have a set of equations that governs the motion of the system. So Lagrange equation of motion, you already saw it, and the kinetic energy and potential energy. And then we can have the equations of motion in a matrix form, as you can see here, with M, C, and G, and F. So M and C are matrices, and G and F are vectors. And then we are doing order reduction, and we have a state variable and the state space representation with x1 and x2. x1 is q and x2 is q dot. And we get the full dynamic system in the form of x dot equals f of x. And this is the full state space representation of the dynamical system. So we have the dynamical system, we have initial conditions, x0, which is where the system starts. And then we need to define what is it an equilibrium of the dynamical system. Equilibrium is a value of the state variables, meaning x, where the state variable do not change. So it's a point where if the system starts in, it will remain in this state. So if you see the dynamical system in a state in an equilibrium, the system does not have velocity. Therefore, x dot has to be 0. And therefore, f of x has to be 0 in equilibrium. So, in a continuous dynamical system, x dot equals f of x. The equilibrium is x such that f of x, or f of the equilibrium state, is 0. And then we need to determine the value of E such that x of t is E, that it is an equilibrium of the dynamical system, meaning in this point f of E is 0. So now that we defined what it is equilibrium, we can talk about the properties of the equilibrium, whether this equilibrium is stable or not stable. If the system will remain there even if I'll move it a little bit, perturb it and move it a little bit, then it will go back or stay in another place or diverge and go to infinity. So we can talk about stability. The first type of stability that we talk about is a uniform stability. So autonomous dynamic system, autonomous meaning doesn't depend on t directly, it depends on f of x. So it's time invariant and there's no forcing input, there's no u. Uniform stability about x equals 0, so the equilibrium will be at 0, meaning that f of 0 is 0. Then for a delta, for every epsilon, as small as I want, there is a delta that the system starts in this epsilon radius environment. There is a delta for which the system never diverges out of this delta equilibrium, delta region. That means that the system is uniformly stable. So it means, I'll show you here, that there is a delta that the system starts within the radius of delta. And over the time, the system move and change the state. This is the state space, x and x dot. So the system moves and it moves to another place. So if this place, this new place that the system moved to is bounded within an epsilon environment, then the system is stable. Yes. And you can see here systems which are stable, it means they are not diverged, but they do not necessarily converge to 0. But they stay within a certain radius of the equilibrium. That means the system is uniformly stable, and it means that it does not diverge. That's the definition. You can see such a system with only 1 degree of freedom that change over time. And you see this system oscillates, but it does not diverge. So it continues to oscillate, but do not diverge. This system is uniformly stable. Then we can talk about asymptotic stability. This is something that if we have a system and we start within a distance from the origin, if times go to infinity, the system state tends towards the origin. That means if I started in any point, eventually I'll get to the origin, which is the equilibrium. And this is an asymptotic stable equilibrium. So it's uniform stability plus this is harder and stronger than uniform stability because now it not only that it does not diverge, it actually converges to the origin. That's the idea of asymptotic stability. It can be local asymptotic stability if it is the system converge only from a certain domain, certain radius from the origin, then it converges for states that are further away, it will not converge. This is local stability. And if for every state it will go into the origin, then it is a global asymptotic stability. For any epsilon, for any radius that I start from, the system will eventually go to the origin, to the equilibrium. Therefore, the equilibrium is globally asymptotically stable. Also, this is for a nonlinear system, as we can see here. For nonlinear system, if F is not linear, then we may have either local or global stability. But if the system is linear, and instead of F, we have x dot equals AX, then the system is either unstable or globally asymptotically stable, or globally stable or globally asymptotically stable. As you recall from control theory, that it depends on the eigenvalues of A, if they are on the open left half plane or not. So asymptotic stability, you see here the state of a dynamical system, which actually converge to some point, and this equilibrium point is asymptotically stable because the state is converging to this point. Okay, for linear systems that we do not have x dot equals f of x, like here, but we have x dot equals ax, A is a matrix, then the system is globally asymptotically stable if the eigenvalues of A are in the open left half plane of the complex plane. So it means that the real part of the eigenvalue of A, of all eigenvalues of A, is smaller than 0. means that it will be in the left part of the complex plane. Such matrix is also called Hurwitz, named after Hurwitz that found this. So for nonlinear system, how we found if it is stable or not. If we have a nonlinear system in the form of x dot equals f of x, and we have an equilibrium of the system x star, such that f of x star is 0, so x dot is 0. So that's the definition of an equilibrium, that x star is such that f of x star is 0. So this is a nonlinear system with an equilibrium. So we can take the nonlinear system and linearize it. How do we linearize it? We define a new linear system, x dot equals ax, where a is the derivative of f according to x. And this is a matrix because f is a vector and x is also a vector of the state space. So we have here something like a Jacobian, a first order derivative of f, and then we substitute instead of x, x star. So we have the matrix, which is a constant now, because we substitute instead of x, x star. So this is the derivative of f at the point x star. So it gives us, you can look at it in like a system with only one variable. So this is like the derivative, like the tangent vector to the curve. So it's first order linear approximation of f. So this is called linear approximation of x dot of f of x at the point x star, at the equilibrium. So we approximate the nonlinear system into a linear system at that point. Like we do in the definition of derivative or Taylor series with only first order and so on. So it's every time it's just the first order approximation. So now we want to discuss stability. Stability of the nonlinear system. And the one that dealt with the stability of nonlinear system was called Lyapunov. He is a Russian mathematician, I think. Yeah. From the University of St. Petersburg, lived between 1857 to 1918. And you can see here is his bio. But he developed all the theory about the stability of nonlinear systems. Okay. So we will talk about two methods of Lyapunov stability. So the first method is about the linearized system. So if the matrix A of the linear approximation system is Hurwitz, meaning that it has eigenvalues in the left half plane, in the open left half plane. Then the equilibrium X star of the nonlinear system, X star is the equilibrium of the nonlinear system. Then we can say two things. First, that the linear system is globally asymptotically stable because the A matrix has eigenvalues on the open left half plane. Therefore, this linear system is globally asymptotically stable. But since it's the approximation of the nonlinear system, we can say that the nonlinear system is only locally asymptotically stable. So there is a certain region around the equilibrium in which if I perturb or move the state to be near the equilibrium, but not exactly at the equilibrium, over the time the system will move and this state will tend to get to the equilibrium and converge to the equilibrium. Is that clear? Okay. So if A has at least one unstable eigenvalue, it means that this eigenvalue of A is in the open right half plane. So it is in the complex plane, it's on the right, not on the left. And it is enough that only one eigenvalue will be there. Then the equilibrium X star is unstable. It's not stable for both the linear and the nonlinear system. So it's enough that the one eigenvalue will be on the right half plane and the whole system is unstable, both the linear and the nonlinear system. Then if the matrix A has no unstable eigenvalues, but it has one or more eigenvalues on the imagery axis, meaning that the real part of the of at least one eigenvalue of the of the approximation, the linear approximation matrix. So the real part is 0. So it means it's on the image, on the imaginary axis. So it's not on the open left half plane and not on the open right half plane. It's in the middle. Then we cannot say if it is stable or unstable. Then it is impossible to determine if the nonlinear system is stable or unstable. So in that case, it's not deterministic. We cannot say. If the system is asymptotically stable, then we can talk about the rate of the convergence of the system. So it means if we want to talk about the rate of convergence, and we want to say that it is converged asymptotically, exponentially, converged exponentially, as you can see here, this is like an exponent curve, and it converges underneath this exponent. It means that the norm, the size of the state space is reduced as function of time with an exponent. The exponent that is actually reduced over time with a negative part in the exponent, like alpha minus alpha. So minus alpha is called the Lyapunov exponent, and this means that the norm of the state space is reduced according to this. If the norm of x of t is contained within an exponentially decaying envelope with convergence, system is exponentially asymptotically stable. So it means exponentially asymptotically stable. Linear time invariant system that is asymptotically stable are always exponentially asymptotically stable, because the solution of linear system, as you learned in control course, the solution is actually something like that with a decaying exponent. So that was up here was the definition of types of stability, and we talked about Lyapunov first method using the linearized dynamical system. Linearized. Now, but if we want to check the stability of a nonlinear system, not through its linearization, we can do this through Lyapunov function, and Lyapunov's second method. So first we define what it is Lyapunov function. Lyapunov function is a scalar function. It's not a vector. It's a positive definite function of the state space of the states. It's V of x. And it is continuous, differentiable function. It is V of x, so it maps from x, the state space Rn, to a scalar function R, which is in R3. Such that V of 0, 0 is the equilibrium, so V of 0 is 0, and V of x anywhere else is positive. So it has a global minimum at the equilibrium. So here are a few examples of Lyapunov functions, which is V of x. Recall that V of x must be greater than 0, and 0 only at x equals 0. So a few examples here. You see the kinetic energy plus potential energy. Yeah. And also some quadratic form of x transpose x, or half of x transpose px, where p is a positive definite matrix. All of these are positive everywhere except of points which are except of the origin. Where x is 0, this function is also 0. Yeah, X transpose Tx. This is also an example. So we can now talk about Lyapunov's second method or second theorem. It means that now we have a dynamical system, x dot equals f of x, and we have a Lyapunov function, v of x is greater than 0, and v of 0 is 0 for everything. So now we evaluate the time derivative of the Lyapunov function along a path of the system, along the trajectory of the system. So we need to take the derivative of v with respect to t. So the derivative of v with respect to t is, if v depends on t, then we have dv to dt. Usually we do not have. But it is dv to dx times x dot. Dv to dt. Dx to dt. And x dot is simply f of x. And that means that we took the derivative along the trajectory of the dynamical system because we substitute instead of x dot, we substitute x. So it's dv to dx times f of x. This is for autonomous systems, systems that do not depend directly on time. So if this dv to dt, dv to dx times f of x, if this is smaller than 0, then the value of v is reduced over time and it decays towards the equilibrium v of 0. As you can see here, it kind of decays. You see here, this is x1, x2. This is the state space, and this is v of x, and v is a positive definite function, as you can see here. Where it is 0 at the origin, and since it's decaying, dv to dt is smaller than 0, then the value of v is being reduced over trajectories of the dynamical system. So if the dynamical system does such loops, eventually it will reduce and get to the origin, which is an equilibrium. And it is an asymptotically stable equilibrium. So if dv to dt is smaller than 0 in the neighborhood of the origin, so it doesn't have to be globally, it doesn't have to be all over the state space, it can be also just local, then the origin is asymptotically stable. This is a sufficient but not necessary condition for stability. It means that if this exists, the system will be stable. And also one more thing is that the Lyapunov function is not unique. V is not unique. I can select many types of Lyapunov function, and if they meet the requirement of Lyapunov function, then then I can use them to prove stability. So to conclude, if v dot, which is dv to dx times f of x, is smaller than 0, then the equilibrium x star is stable. Why is stable? Because if it's 0, then it means that it does not decay, does not reduce, and stay in the same level set of v. So it does not diverge, but not necessarily converge. But if v dot is actually smaller than 0, is negative, then the equilibrium point is asymptotically stable. So it will decay to the origin. And one more thing is that if v is greater than 0 for certain region, and v dot is smaller than 0 in this region, then the equilibrium will be asymptotically stable within this region. So everything that will start within this specific region will end up at the origin. So if v dot is strictly smaller than 0, then the equilibrium x star equals 0 point is asymptotically stable. And if v of x goes to infinity when x goes to infinity, then x star equals 0 is globally asymptotically stable. So if all of this holds true everywhere, then the system will be stable, asymptotically stable globally. And we can take it, so we started with just the stability when v dot is 0. Then we went to start something that is a little stronger, which is if v dot is negative, strictly negative, everywhere, and v of x goes to infinity with x goes to infinity, then it's globally, so it's even stronger. And now we can talk of something even stronger, which is the rate of the convergence. So if v of x is a candidate Lyapunov function that meets the requirement of a Lyapunov function, and v of x is greater than k1 times the norm of x to the power of p, and smaller than k2 times the norm of x to the power of p, and v dot of x is smaller than minus k3 times the norm of x to the power of p, where k1, 2, and 3 are positive constant, then the equilibrium x star equals 0 is exponentially stable. And if the conditions, all those conditions are met for every x, then the stability is also, the exponential stability is also global exponential stability. I think we'll do the example after the break, after the recess. Okay? I'll pause the recording. Okay, we'll continue with an example. So we're taking a very simple example. This is a mass with a spring and damper. We can write the dynamics as mq double dot plus bq dot plus kq, where b is the damping coefficient, k is the spring coefficient, and that equals 0. This is the dynamics of the system. Then we do state space representation. So we reduce the order, but now we define x1 equals q and x2 equals q dot. Therefore, x1 dot is x2 and x2 dot is q double dot. So it is, we can move everything to the right hand side. So it's minus k divided by n of times q, which is x1, minus b divided by n, and times q dot, which is x2. So this is the first order dynamical system, which is 2 times larger. The first order dynamical system is only with 1 degree of freedom. Now we have 2 degrees of freedom, 2 state space variables instead of 1. We can take a Lyapunov candidate function, v of x, such that it is half mx2 to the square mx2, plus half k square of kx1. And see, this is exactly the kinetic energy and the potential energy of the spring. So it is energy. It's positive everywhere. And it is 0 only when x1 and x2 are 0. So this is a Lyapunov function. It's positive everywhere and 0 only at the origin. And also, you can see that the origin x1 and x2 0 is an equilibrium point, because if I substitute here x1, x2 0, then x dot will be 0. So it is a positive, it is x equals 0 is an equilibrium. Now we can check if this equilibrium is stable or not. So we have the dynamical system, we have the Lyapunov function, and now we need to take the derivative of Lyapunov function along trajectories of the dynamical system. So it means that we do dv to dx times x dot. So dv to dx, dv to x1 is k, x1 is kx1 times x1 dot, and x2 dot, which is here. Now we can substitute x1 dot and x2 dot from the dynamical system on top. So x1 dot is x2. x1 dot is x2, as you can see here. And x2 dot is minus k over n x1 minus b over n x2, and all of this is multiplied by n x2. So what do we have here? M and n is canceling out, and we are left with minus k x1 x2 plus k x1 x2. See, minus k x1 x2 plus k x1 x2. So this cancel out. And we have only minus b x2 squared. Minus b x2 squared. And minus b x2 squared, because it's squared, then it is negative. It's negative everywhere except the 0, which is good for us. We wanted that v will be strictly negative. That's a thing. But we do have a problem here, because v dot depends only on x2. It does not depend on x1. So I don't know how it varies with respect to x1. And therefore it won't be strictly negative for every x dot x1 x2 equals 0, because it does not depend on x1. In that case, we need to take into account the dynamical system and see how the dynamical system behaves. And there is a principle called Lassalle's invariance principle that dictates how the system behaves in such case that v dot does not depend on the entire space, on the entire state space, x1 and x2, but only on part of it. So when v dot is smaller or equal to 0, we use Lassalle's invariance principle. So we have a dynamical system. Was disconnected. Yeah, it's recording. Oh. Oh, it's recording on this computer, not to the cloud. It's too bad. And we say that the solution for the dynamical system is called S. Then we define a limit set, omega, as the set S of all the solutions to the dynamical system, is the omega limit set of a trajectory S if for every y that is in S, there exists a strictly increasing sequence of times t such that S of t is going to y as t goes to infinity. So it means that there is a limit set that the system is stayed in this limit set and does not diverge. And this is the invariant set. The set N is said to be an invariant, a positive invariant set if for all y that are in N and T0 is 0 is greater than 0, we have the solution of the dynamical system that is in M as well. So this means invariant set that if I start in this set, I end up in the same set. It may be proved that omega limit set of every trajectory is closed and invariant. So this set is closed and invariant, so it means all solution get is inside. We may now state the LaSalle principle. And the LaSalle principle says that let V be a locally positive definite function such that on the compact set omega we have V dot E smaller or 0, smaller than 0 or 0. Then we define S as the set where X is in omega, which omega is a compact set such that V of X is smaller than C and V dot is 0. So we take all the points that meets all X's that in which V dot is 0. So now we look only on the set where V dot is 0. As t goes to infinity, the trajectory tends to the largest invariant set inside S, inside this set, where V dot equals 0. Its omega limit set is contained inside the largest invariant set in S, in the solution to the dynamical system. In particular, if S contains no invariant set other than X equals 0, then 0 is asymptotically stable. So I'll show you how we implement this. Now, we look, in our case, we have X dot, we have V, and we have V dot, which is minus Bx2 squared. Now, we look at the set where V dot is 0. Where V dot is 0 when X2 is 0. So S will be the set X1, X2 such that X2 is 0. This is the set where V dot is 0. This is S. Now we look how the dynamical system behaves in this set. So we substitute X2 equals 0 into the dynamical system. And we have this dynamical system. X dot equals minus K X1. But this system will not stay anywhere unless X dot is 0. So the largest invariant set in S that the system will stay in is where X dot equals 0. This will happen where when minus K over N is X1, that times X1 will be 0. And that requires that X1 will be 0 as well. And therefore, the largest invariant set in S that the system will be in is x2 equals 0 and x1 equals 0. Because otherwise, we will have x dot, and the system will diverge, and we'll have x1 and x2. Eventually, will evolve over time. Therefore, according to Lassalle's principle, this invariant set where x1 and x2 are 0 is the largest invariant set of the system, and the system is asymptotically stable. Did you understand? Now, in particular, we can use Lyapunov's second method on a linear system or on a linearized system. So if we have an original nonlinear system, x dot equals f of x, and we have an equilibrium at the 0 such that f of 0 is 0, and that means that x star, the equilibrium point, is at 0. Then the linearization of this dynamical system is x dot equals ax, where a is the derivative of f with respect to x when we substitute x star. So we substitute x equals 0 because x star is 0. Okay? So now we have a linearized dynamical system. We can choose a candidate Lyapunov function. And we define an arbitrary positive definite function v of x as a quadratic function x transpose px, where p is a symmetric positive definite matrix. It means that all its eigenvalues are positive, strictly positive. And if all its eigenvalues are positive, then P, we denote this with this kind of sign. It's not, it's like greater than, but like rounded, because it's matrix. It's not a scalar. It's P matrix greater than 0. So it means that P is symmetric positive definite, and that means that the quadratic function of P, x transpose Px, will be positive, strictly positive, for every x except of x equals 0, where v is 0, and therefore v transpose Pv is greater than 0 for every v that is not 0, and for 0 is 0, and therefore this is a Lyapunov function that meets the requirement for Lyapunov to be positive definite everywhere except of at the origin, which is the equilibrium point. Now, we would like to take the derivative according to Lyapunov's second method. We would like to take the derivative of v with respect to time. So it's dv to dx times dx to dt. dv to dx times x dot. So it's the derivative of x transpose px, which is a multiplication of two functions, x transpose and x, which are depends on time. So it's x dot transpose times px plus x transpose px dot. So we have here x dot and here x dot. But x dot in our linear system is ax. So we substitute x dot equals ax to get the derivative and the solution of v dot along the trajectories of the dynamical system. So we have v, we have the derivative of v, and we substitute instead of x dot ax, so we have ax transpose px plus x transpose p times ax. And if we open this, we get x transpose times a transpose because we change the order and then put transpose on both. So it's x transpose a transpose p, px plus x transpose pax. And we can take out the x transpose from the left and x from the right. And we have here in the parentheses a transpose p plus pa. And we want to see if this, which is v dot, if it's negative. So we have this v dot. And now we want to say something about the term here, a transpose p plus pa. So if we can find a matrix Q such that this a transpose p plus pa equals minus q, and q is positive definite, or q is positive definite. So if something like that exists, then I can replace this term with minus q, and I get minus x transpose qx. And since q is positive definite and I have minus here, then the whole term here will be negative, strictly negative for every x that is not zero. And therefore the system will be asymptotically stable. So if I can find such q that meets this Lyapunov equation, then the system will be asymptotically stable. It's not always exist, but many times yes. So we need p, which is positive definite, and q, which is positive definite, that solve this Lyapunov equation. And there is a function in MATLAB that actually solves Lyapunov equation numerically and tell you if there is a solution or not. So this is how we find if a linear system is stable. We can look at the eigenvalue, but we can also solve Lyapunov equation. And if there is a solution for Lyapunov equation, then the system is stable. So we choose Q, which is the positive definite matrix, and solve Lyapunov equation to get P, which is also positive definite matrix. And then V dot will be 0 and the system will be asymptotically stable. Now we want to get into control. So I have a dynamical system and I want it to follow a desired path, a desired trajectory. So I have a dynamical system with M, C, and G, and a control input Q. And I have a trajectory, a desired trajectory, Q D of T, Q dot D of T, and Q double dot D of T, where I want the system to follow this trajectory, and I'm looking for what U should be. What should be the input to the dynamical system such that it will follow the desired trajectory. We also have initial conditions where the system starts. Q0, QD0 is also 0. QD is 0 and Q0 are the same. And Q dot at 0 at time 0 is also Q dot D at time 0, and so on, Q double dot. So it means that the system starts at time 0 on the desired trajectory. Then, if we take the control input to be and Q double dot desired plus CQ dot desired plus G, which is identical to the dynamical system, but only with the desired trajectory, then the system will follow the desired trajectory. Oh. Why is that so? Because if I put this here, so, and this is U, I put this here, and I start at this, I'll get 0 equals 0. Okay? So I'll meet the dynamical system. And then I can follow this over and over. And then I'll get, every time I'll get the whole dynamical system will be canceled out, and I'll follow the desired trajectory precisely. So that's good. But this is called open loop. I have no knowledge of the system. The input depends only on the desired trajectory. But for this, I need to know the matrices M, C, and G exactly. And I have to be on the desired trajectory exactly. So I cannot have any errors, because if I do have error, I will get off the desired trajectory. I will not meet this equation, the dynamical equation, and the system will diverge. So that's the problem with open loop control. So this is the input that I need in order to follow the desired trajectory, but there is nothing here, no term that will cause the system to get back to the desired trajectory if it just get off this desired trajectory. And in order to do that, we are introducing the feedback linearization method. It's sometimes called PD, proportional and differential controller, plus inverse dynamics. So if I have the same dynamical system as before, and I have this input, but instead of writing MQ double dot alone and CQ dot desired, I have here this MQ Q double dot desired, which is the same as before, but I have here two terms which depends on the error from the desired path. And here I have another term, the C Q dot plus G, which I require I can measure Q and Q dot. So I can measure this. And I have here two terms. Here, this is the feed forward. So I kind of expect what to do and then give another boost to the input in order to get to the desired trajectory. This and the end. And we have here these two terms that depend on the error between the current state and the desired state, and they are the feedback that actually gives some effort in order to get the system back to track if it diverges from the track. So now we can analyze the stability of this system. So if I substitute U into the dynamical system, what I get is, you see here, MQ double dot minus MQQ double dot desired. So it's like ME dot double dot. And then I have those, and when I take this to the left side, I'll get plus K1 E dot, KD E dot, plus KPE, this transfer to the left side. And the rest, simply this and this cancels out. The C and CQ dot from the right and from the left cancel each other, and G also cancels the G to the left. And I left with only this dynamical system of the error system. Error of Q minus Q desired. M is symmetric positive definite, so I can multiply both sides by the inverse of M, and I get E double dot plus KDE dot plus KPE. This is the dynamical system of the error after I applied the input U. Now, if this system is stable at 0, at E equals 0, it means that if I start from a point where E is not 0, it will converge to 0. And if E is 0, then the system is on the desired trajectory. That's the meaning. So I want to prove that this dynamical system is stable at 0, at E equals 0. So this is the closed loop system of the error. And we can write this. This is the second order. We can reduce the order. and write it as a state space representation of E dot. So E dot is E2. It's this E dot. And E double dot here is minus KPE minus KDE dot. Minus KPE minus KDE dot. So I have here a dynamical system where I have X dot equals AX. So it's a linear dynamical system. And we have a matrix A here of the dynamical system. So we want to see when this system is stable, asymptotically stable. And if it's asymptotically stable, then it means that if I start with E equals 0, with Q equals Q desired, then the system will remain on E equals 0. So it will follow the trajectory of QD. That's the idea. So now what left to prove is that A is a stable matrix. So all of its eigenvalues are in the open left half plane. Or what are the conditions for Kp and Kd such that A will have eigenvalues on the open left half plane. So this is our dynamical system on the right here. And now we need to see what are the conditions on Kp and Kd. Now we start the proof with an assumption that lambda is an eigenvalue of A. And lambda can be complex number. And for lambda, this eigenvalue, we have a compatible eigenvector V, which is V1 and V2, which also can be complex. And from the relation between the matrix and the eigenvalue and eigenvectors, we know that AV equals lambda V, where lambda is an eigenvalue and V is an eigenvector, a compatible eigenvector. So now we look at lambda V, lambda V1, V2, and lambda is an eigenvalue of A, and therefore lambda V equals AV. So this is AV. So lambda V equals this term, means minus Kp V1 minus Kd V2, and V1 is equals to V2. Lambda V1 is equals to V2. Now, this is for any eigenvalue of n eigenvectors of A. So now, let's assume that lambda is 0. If lambda is 0, then we have lambda V1 equals V2. Therefore, V1 lambda is 0. Therefore, lambda is 0 here. Therefore, V2 lambda V1 is 0, and V2 must be 0. And if V2 is 0, then lambda V2 lambda is 0. lambda v2 is 0, so v1 must be 0. Okay. And therefore v1 is 0. So we got, for lambda 0, we got an eigenvector which is 0. This is the trivial solution, and it cannot be. And therefore lambda equals 0 is not the negative value of A. Otherwise, we'll get V, which is not a trivial solution. So lambda equals 0 is not a solution. So if lambda is not 0, then if V2 will be 0, if V2 will be 0, then lambda V1 will be 0 and also V1 will be 0. Then, therefore, V2 must not be 0. And also V1 cannot be 0, otherwise we'll get the same solution. So we can suppose now, since V, we can change its length, actually, not its direction, but its length, and we can parameterize it in a single parameter. When you probably remember in algebra that eigenvector, I can multiply it by any constant, and it will still be an eigenvector. Therefore, I can assume that the length of the V1 part will be 1. Just an assumption without loss of generality. It can be any number that I want. Then lambda square is V, how do I get there? This lambda V1 times lambda V1 times V1, the complex conjugate of V1, and V1 length is 1. Therefore, V1 times V1 is 1. Is the length. If I take the conjugate transpose of V1 times V1, this is the length of V1. And the length of V1 is only 1. Therefore, I can write like this, and this equals to lambda squared. So lambda squared times V1 conjugate transpose times V1. This is the length of V1, which is 1. Okay, but lambda V1 is from here, it's lambda V1, it's V2. So I can substitute here lambda V1 equals V2 from the dynamical system. And therefore, I get V1 conjugate transpose times V lambda V. I get, lambda V2. And so 1 lambda V1 is in the V2. Okay. Now we can continue this. So we took lambda squared and we got here. Now V2, lambda V2 is minus KT V1 minus KD V2 from the dynamic consistent. So I can substitute instead of lambda V2, this thing. And then I get here V1 conjugate transpose times KT V1 minus, now I take, instead of V2, I substitute lambda V1. So I have lambda V1 conjugate transpose KD V1. So I have here two terms which are quadratic forms of KP and KP. And we get to this. Lambda squared equals this term that we reached. Now we define two values, alpha and beta. Alpha is V1 conjugate transpose KP V1, and beta is V1 conjugate transpose times KD V1. And if KP and KD are positive definite matrices, which have positive eigenvalues, then this alpha and beta are positive, strictly positive, for every V which is not zero. And V1 is not zero, because we set V1, the length of V1 to be zero. And we get from here lambda squared plus, now V1 KP V1, I take everything to the left half, to the left side of the equation. So it's lambda squared plus beta plus beta lambda, beta is this, lambda, plus alpha here equals 0. And alpha and beta are positive. So now I have a quadratic equation with lambda as the unknown. And I can solve it as I solve simple quadratic equation. So I have minus beta plus minus beta squared minus 4 alpha, everything divided by 2 times 1. And it means that the real part of this will be smaller than 0 in order for lambda to be on the open left-hand plane. Because lambda can be complex. And lambda is the eigenvalue of A. Lambda, this lambda is the eigenvalue of this matrix. So I look at this. Alpha is positive. Beta square, I have beta square here, minus 4 alpha. This can be, since beta and alpha are positive, that can be either real or complex, either greater than 0, this part, or smaller than 0. If it's smaller than 0, then this part is the complex, because I have square root, so this part will be complex. And the real part will be minus beta over 2. So the real part will be negative. But if this is this beta square minus 4 alpha is positive, then since alpha is positive, this will be smaller than beta square. And if this term will be smaller than beta square, the square root of this will be smaller than beta. So when I have minus beta plus something here, which is positive, but is smaller than beta, it will still be negative, all this real part. And therefore, anyhow, if beta and alpha are positive, then the real part of lambda will be negative. And therefore, if the real part of lambda is negative, then this matrix will have eigenvalues on the open left half plane. And if it has eigenvalues in the open left half plane, then this dynamical system is stable, topically stable. So the condition is that the conclusion is that if we select KT and KD that are positive definite, such that alpha and beta are positive. If they are positive definite, then alpha and beta are positive. Then for this input, the dynamical system, this control law, actually this input, then it's guaranteed that the error will converge to E equals 0 because it's a stable state of the error dynamical system. And we will get a perfect trajectory followed. Even if I have error from the trajectory, it will get back to the trajectory. So it's a very good and useful controller. But we have one major problem, major disadvantage, that the controller depends on N, C, and G. And if I don't know them perfectly, then I still have a problem because those terms will not cancel out the terms in the dynamical system. And the whole proof here will not hold because I will have something from the original dynamical system and I cannot cancel terms and the proof is wrong and the whole system may diverge. So that's a major problem, a major disadvantage. So what we'll do, we'll see how we can look at this without the feedback, without the inverse dynamics, without the term of NCG, and have only the proportional and differential terms. This will do after the break. Let's continue. So now that we saw the disadvantage of having to know precisely M, C, and G, let's try do that without them. So assume that we have a dynamical system without gravity. We'll talk about gravity later. So M Q double dot C Q dot equals U. And we have a proportional and differential controller such that U have term minus Kp times the error minus Kb times the error dot. And let us check the stability around the set point such that the equilibrium will be Q equals Q desired and Q dot desired will be 0. So the system will stop at the equilibrium. So if I put this, then I have Q desired here, Q dot desired is 0. So the Q desired will cause U to be 0, and therefore Q dot and Q double dot will have to be 0 as well. Therefore, this will the point Q desired 0, Q desired and Q dot equals 0 is an equilibrium. And we want to check if it is a stable equilibrium. So at the set point, if the system will reach this set point. So it's no longer trajectory following, it's no longer following a specific trajectory, it's just getting into a point. So in one term, it may be stronger because we can prove the stability, but it is weaker from the PD plus time inverse dynamics because it's only stability for a set point and not a stability for trajectory following. So we choose a candidate Lyapunov function, which is the kinetic energy of the system. Recall that the kinetic energy is half Q dot transpose and Q dot. And the potential energy of the controller, of the proportional part of the controller. The controller here acts as a spring and damper. The proportional part is like a spring. It applies force which is proportional to how much I moved from the set point, from Q desired. So it's like a spring. And Kd, which is multiplied by Q dot, is like a damper that acts to reduce the speed, the velocity. So it's like a spring and damper. This is a PD controller. So a spring has a potential energy which is Q transpose Kp Q. But here we have Q minus Q desired, this because we have a different set point for the for this spring. So we have half Q minus Q desired transpose Kp Q minus Q desired, and Kp is a positive definite matrix, as we saw in the previous solution. So we have this candidate Lyapunov function, and we need to see if this set point of Q equals QD and Q dot D equals 0, if it is a stable equilibrium. So I need to take the derivative of V, of the Lyapunov function, with respect to time along trajectories. So on the right, I have the dynamical system, the input, the controller, and the Lyapunov function. And Kp and Kd are positive. Then I take the derivative of V. V is this. So taking the derivative of V with respect to Q and Q dot. So taking the with respect to time, actually, not Q and Q dot, with respect to time. So the first term depends on Q dot transpose and Q dot. So it's Q dot transpose and Q double dot, and then Q double dot transpose and Q dot. This is the derivative of this term, the first term. Also, M is also depends on Q. In general term, M is a matrix which depends, the inertia matrix depends on Q. Therefore, Q depends on T, on the time. Therefore, I need to take the derivative of M with respect to time. So I have Q dot transpose M dot Q dot as well. And these three terms are just the derivative with respect to time of the first term of V. Next, I need to take the derivative of the term of Kp. So it's the derivative of this first term is the derivative of Q minus Qd is Q dot only, because Qd is constant. Therefore, I have Q dot transpose times Kp times Q minus Qd plus half of Q minus Qd transpose here plus Kp times the derivative of Q minus Qd, which is Q dot. Maybe I'll put it. No. Then I have the next line here. So since M is symmetric positive definite, therefore Q dot and Q double dot and Q double dot transpose and Q dot is the same. So I have half here, because the transpose is the same. And we get Q dot transpose and Q double dot. Then we have plus half Q dot transpose M dot Q dot. Plus, this is also Kp is symmetric positive definite, and therefore this term and this term are the same because they are transpose of one another. And this is also a scalar here. So transpose of scalar is a scalar. And so I can take this transpose of this, which will be this. So I have twice this term, which is Q dot transpose Kp, Q minus Qd trans Qd. Then I need to substitute, instead of M Q double dot, the dynamical system there, which is U minus CQ dot. So I have U here. This is U. Kp times Q minus Qd minus Kd Q dot. This is U. And I have minus CQ when I move it to the other side. and this is multiplied by m, this term. And what else? Yeah, and q double dot is u minus cq. So I have m minus m times m to the minus 1. So this also, this term is also the identity matrix. And I have the term with m dot here, exactly the same, and the term with kp here, which is exactly the term of kp here. But at the beginning, it's with minus. We have minus q dot transpose kp q minus qd. And here I have plus q dot transpose kp q times q minus qd z. So this cancels out each other. And I'm left with q dot transpose times minus cq q dot minus kd q dot and plus half m dot q dot. So I have minus c plus half m dot minus kd, and I have q dot at the end. But recall that m dot minus 2c is an antisymmetric matrix. And therefore, any quadratic form of m dot plus minus 2c will be 0. So I have here a quadratic form, q dot transpose times minus c plus half m dot times q dot. And since m dot minus 2c is antisymmetric, this entire term is simply 0. And therefore, I left with minus q dot transpose kd q dot. And this is a quadratic form of kd. And if I choose kd to be a positive definite matrix, this v dot will be negative. And this is what we want to prove. kd is positive definite for all q dot, which is not 0. And therefore, minus q dot transpose kd q dot is strictly negative for every q dot which is not 0. So this is almost good because v dot depends only on q dot and not on q. Therefore, I need to use here LaSalle invariant principle. Yeah. So we apply LaSalle's invariant principle for the set v dot equals 0. And for v dot equals 0, this is v. And v dot is minus q dot transpose kd q dot. So for the set where v dot equals 0 is when q dot is 0. So this set of q dot equals 0 is such that when I substitute q dot equals 0 to the dynamics of the system, so q dot is 0, and mq double dot is also 0, and in u, q dot is 0, q dot desired is also 0, and I have only this term here, minus Kp Q minus Q desired equals 0. This is the term here. And this is true only when Q is Q desired. Therefore, the largest invariant set in this S will be the set where Q is in Q desired and Q dot will be 0. And therefore, the system will be asymptotically stable for Q dot equals QD and 0. And this proves the stability of the PD controller. And this is good because it means that if the system starts from any initial condition and then it will get eventually, after some time or infinite time, it will get to the set point of Q equals QD and Q dot equals 0. So it will stop at the point that we want it to stop. We didn't talk about that we took a dynamical system without gravity. If I take the gravity works as another potential here. And it applies some offset on the Q desired. So it will not converge to Q desired. It's like connecting two different springs. So it will move a little bit until it will get to, it will converge to a point which is not a QD, but it's something near the QD. So this is so there will be some offset from the point that we want to reach. Another thing is that this is stability to a set point, around the set point. But if I want to move along the trajectory, I have a problem because I didn't prove the stability for a trajectory point. So what we are doing, we are treating the system. We take a set point on the trajectory that we want to follow. Then the system tends to get to this set point. And just before it gets there, we move the set point along the trajectory. And then it continues to this point. So if I have the system tries to get to the set point, and then just before it reaches the set point, I move the set point further, and the system tries to get to the new point. And therefore, I move the set point all the time. And this is kind of tricking the system to follow a path. There's no proof for that, but in practical system, this works and works pretty good. And sometimes we also add another term for integral part. So another term that takes the integral part of the error and therefore close the gap, the offset that is caused due to gravity or due to any other disturbance. Any questions? So this is the end of this part. I'm not sure if you want to continue, or that's enough for today. It was kind of too mathematical class. Yeah, so I think we'll leave the rest for next week. But this is the important part of using PD or PID controller. And this is very important because this PD or PID is the most useful controller in control theory and practice, actually. You don't need to know the system itself. You just need to tune the proportional and differential gains. So it's very simple and very useful, and it works. Works in practice. Okay, so that's it for today, and we'll continue next week.
תודה רבה, אמיר.
אין בעד מה.